One of the better known multiplication technique is discussed in Chapter 4.1, Multiplying by 11. Multiplying a two-digit number by 11 is particularly easy. Let's take a look at an example. 35 times 11. To multiply 35 by 11, first we split the two digits, 3 and 5, and then we insert the sum of the two digits. 3 plus 5 is equal to 8. 35 times 11 is equal to 385. We can also multiply longer numbers by 11. If, for example, we have 34,532 times 11, we first bring down the first digit 3. Then we add it to the digit next to it. 3 plus 4 is 7. 4 plus 5 is 9. 5 plus 3 is 8. 3 plus 2 is 5. And then we bring down the last digit 2. 34,532 times 11 is equal to 379,852. To check the multiplication by 11, we can use the alternate sum method. The alternating sum of the digits of multiples of 11 is always equal to 0 or a multiple of 11. To find the alternate sum, we can add and subtract alternately the digits of the product, or sum up the alternating digits before taking their difference. Chapter 25, Special Multiplication, Multiplying by x plus 1. If you think of x as 10, then multiplying by x plus 1 is similar to multiplying by 11. We can therefore use the technique that we used previously in multiplying by 11 to multiply by x plus 1. Let's take a look at the example. 4x plus 3 times x plus 1. This is very similar to multiplying by 11 a two-digit number. So the first step would be to split the two terms, 4 and 3, and since we're multiplying by x plus 1, the degree of x is increased by 1. So 4x now becomes 4x squared. And then we insert the sum of the coefficients of the two terms. 4 plus 3 is 7. So 4x plus 3 times x plus 1 is equal to 4x squared plus 7x plus 3. We can also multiply longer polynomials by x plus 1 in the same manner that we can multiply longer numbers by 11. Example, 2x cubed plus 5x squared plus 3x plus 4 times x plus 1. We bring down the first coefficient, 2, increasing the exponent of x by 1, so now it's 2x to the fourth. Then we add this to the coefficient of the term next to it. 2 plus 5 is 7, 5 plus 3 is 8, 3 plus 4 is 7, and then we bring down the last digit, 4. 2x cubed plus 5x squared plus 3x plus 4 times x plus 1 is equal to 2x to the fourth plus 7x cubed plus 8x squared plus 7x plus 4. In Chapter 4.2, we extend the knowledge that we have in multiplying by 11 to multiply 12 by 12 and 13. Let's take a look at an example. 213 times 12. First, we bring down the first digit 2. Then we'll multiply the digit on the left by 2 before adding it to the digit next to it. 2 times 2 is 4 plus 1 is equal to 5. We can do this to the next one. 1 times 2 is 2 plus 3 is equal to 5. Then we multiply the last digit by 2. 3 times 2 is equal to 6. 213 times 12 is equal to 2,556. We can check our multiplication using the digit sum check based on the Vedic Sab Sutra. The product of the sums is equal to the sum of the product. So we can find, let's take a look at the left-hand column first. We can find the digit sum of 213 by adding 2 plus 1 plus 3, and the digit sum of 12 by adding 1 and 2. 2 plus 1 plus 3 is equal to 6, and 1 plus 2 is 3. Multiplying them, we get 6 times 3 is equal to 18. We can find the digit sum of 18, that's 1 plus 8 is 9. Then let's move to the right-hand column. Let's find the digit sum of 2556. 2 plus 5 plus 5 plus 6 is 18. Again, if we add 1 and 8, we get a 9. Since both have the same digit sum, then our multiplication is most likely correct. Now let's take a look at another example. This time we'll be multiplying by 13, but we'll be using the extended method of multiplying by 11, same as what we did with multiplying by 12. But of course, this time, instead of multiplying by 2, we'll be multiplying by 3, because 13 is 3 above 10. So we have 213 times 13. We bring down the first digit 2, then we multiply the digit on the left by 3 before adding it to the digit next to it. So 2 times 3 is 6, plus 1 is equal to 7. 1 times 3 is 3, plus 3 is equal to 6. Then we'll multiply the last digit by 3. 3 times 3 is 9. 213 times 13 is therefore equal to 2,769. We can also check our multiplication by 13, same as what we did with multiplying by 12, using the digit sum check. So again, let's look for the digit sum of 213 and 13. 2 plus 1 plus 3 is 6, and 1 plus 3 is 4. 6 times 4 is 24. Adding 2 and 4, 2 plus 4 is 6. So now let's move to the right-hand column. What is the digit sum of 2769? 2 plus 7, we can cast out 9, and then 2 and 7, and then we're left with 6. Both sides have the same digit sum, 6, so most likely our multiplication is correct. We have previously extended the multiplication technique by 11 to multiplying by 12 and 13, and to multiplying by x plus 1. So similarly, as we have extended multiplying by 11 to multiplying by 12 and 13, we can extend the technique for multiplying by x plus 1 to multiplying by x plus any constant a. So for example, if we have 3x cubed plus 4x squared plus 2x plus 5, and we want to multiply it by x plus 3, we can use the same technique as multiplying by 13. We bring down the first coefficient, 3, again increasing the exponent of x by 1. Then we'll multiply the digit on the left by 3 before adding it to the digit next to it. 3 times 3 is 9, plus 4 is equal to 13. 4 times 3 is 12, plus 2 is equal to 14. 2 times 3 is 6, plus 5 is equal to 11. Then we multiply the last digit by 3. 5 times 3 is equal to 15. 3x cubed plus 4x squared plus 2x plus 5 times x plus 3 is equal to 3x to the 4th plus 13x cubed plus 14x squared plus 11x plus 15. Chapter 6.1 Dividing by 9. Long numbers can be divided by 9 by getting the running sum of the digits of the number. Example, 321 divided by 9. First, we bring down the first digit 3, then we add this to the next digit. 3 plus 2 is 5. Then we add this resulting sum, 5, to the last digit. 5 plus 1 is 6. The last sum is the remainder. So 321 divided by 9 is equal to 35 remainder 6. Let's take a look at another example. If, for example, we have 1,253 divided by 9. Again, we bring down the first digit, 1. Add it to the next, 1 plus 2 is 3. Then we add a 3 to the next digit. 3 plus 5 is 8. Then we add a 8 to the last digit, 3. 8 plus 3 is 11. The last sum is the remainder. But we see that 11 is still bigger than 9 and may still be divided by 9. 11 divided by 9 is 1 remainder 2. So 138 remainder 11 is the same as 139 remainder 2. In the same manner that we have divided by 9, we can divide by x minus 1. This is discussed in Chapter 27, Special Division, dividing by x minus 1. So our example here is 2x cubed minus x squared plus 3x plus 2 divided by x minus 1. Again, we first bring down the first coefficient, 2, and this time, since we're dividing by x minus 1, the exponent of x is decreased by 1. Next, we add the 2 to the next coefficient. 2 plus negative 1, or 2 minus 1, is 1. So now we have plus x, or 1x. So next we have 1, then we add it to the next coefficient. 1 plus 3 is 4. We add 4 to the next coefficient. 4 plus 2 is 6. The last sum again is the remainder. So it's remainder 6. 2x cubed minus x squared plus 3x plus 2 is equal to 2x squared plus x plus 4, remainder 6, or if you want to write it as, you may also write it as 2x squared plus x plus 4 plus 6 over x minus 1. Chapter 7.1 is about dividing by 11. This is very similar to dividing by 9. Long numbers can be divided by 11 by getting the running difference of the digits of the number subtracting the previous answer from the next digit. So in dividing by 9, we were getting the running sum, but when dividing by 11, this sum will be getting the running difference. Let's take a look at an example. 234 divided by 11. We bring down the first digit, 2. Then we subtract. 3 minus 2 is 1. So we're subtracting our answer, our difference, from the number on the right. So the last one would be the remainder. The last difference would be the remainder. 4 minus 1 is 3. So it's 21, remainder 3. 234 divided by 11 is 21, remainder 3. This method of dividing by 11 may also be used to divide by x plus 1, as discussed in chapter 28. So let's take a look at an example. 2x cubed minus x squared plus 3x plus 2 divided by x plus 1. So again, we copy the first coefficient, 2, decreasing the exponent of x by 1, since we're dividing by x plus 1. So 2x cubed now becomes 2x squared. And then we subtract. Negative 1 minus 2 is equal to negative 3. 3 minus negative 3 is positive 6. 2 minus 6, the last difference would be the remainder. 2 minus 6 is negative 4, so its remainder, negative 4. 2x cubed minus x squared plus 3x plus 2 divided by x plus 1 is 2x squared minus 3x plus 6, remainder, negative 4. Or you may also write it as 2x squared minus 3x plus 6 minus 4 over x plus 1. Chapter 34.1 discusses some special cases. Particularly for this one is when one factor is x plus 1. We have learned earlier that the alternating sum of multiples of 11 is always equal to 0 or a multiple of 11. The same is true for multiples of x plus 1. The sum of the coefficients of the odd-powered and the even-powered terms of polynomials are equal for all multiples of x plus 1. So getting the alternating sum would yield 0. For quadratic expressions, this simply means that the coefficient of the x term is equal to the sum of the coefficient of the second degree term and the constant. Let's take a look at an example. Factor 2x squared plus 5x plus 3. The sum of the coefficients of the odd-powered terms is equal to the sum of the coefficients of even-powered terms. We can see here that 2 plus 3 is 5, which is actually the middle coefficient. Therefore, x plus 1 is a factor of 2x squared plus 5x plus 3. Now we'll look for the other factor. We can use the first by the first and the last by the last to find the other factor. So we divide them by x plus 1, since one other factor is x plus 1. 2x squared divided by x is equal to 2x, and 3 divided by 1 is 3. So the other factor is 2x plus 3. 2x squared plus 5x plus 3 is therefore equal to x plus 1 times 2x plus 3. For any trinomial ax squared plus bx plus c, If one of its factors is x plus 1, then the other factor is ax plus c. Let's take a look at another example, a longer polynomial. Factor 4x squared plus 13x squared plus 4x minus 5. Again, we see that the sum of the coefficients of the odd-powered terms is equal to the sum of the coefficients of the even-powered terms. 4 plus 4 is 8. In the same manner, 13 minus 5 is also 8. Therefore, x plus 1 is a factor of the polynomial. We can again apply the first by the first and the last by the last. Applying those, we get 4x cubed divided by x is equal to 4x squared, and negative 5 divided by 1 is negative 5. The other factor, therefore, is 4x squared plus bx minus 5. Now we don't know yet what b is. So this sum will be determining b. We may use the product of the sums is equal to the sum of the product to determine experimentally b. So we add the left hand side, 4 plus 13 plus 4 minus 5. So we get 16, and then on the other side we add the coefficients. The coefficient of x is 1, 1 plus 1 is 2, and then 4 plus b minus 5 can be simplified into b minus 1. So that would lead to 2 times b minus 1 should be equal to 16, right? So that means that 8 is equal to b minus 1, or b is equal to 9. But there are other ways to find the other factor. So we get that 4x cubed plus 13x squared plus 4x minus 5 is equal to x plus 1 times 4x squared plus 9x minus 5. There are also a lot of other ways to find experimentally b. We can use what is called argumental division, which is actually the reverse of the general multiplication method, or the vertically and crosswise method of multiplication. So using that, we know that 4x times 1 plus bx times x should be equal to 13x squared. So simplifying that, we get 4x squared plus bx squared is equal to 13x squared. Simplifying further, we do 13 minus 4 is equal to b, so b should be equal to 9. We may also we can also find b by thinking of it as a reverse of multiplying by 11. So remember, you have 4. What do you need to add to 4 to make it 13? So you're supposed to add 9. Therefore, the coefficient of x should be 9. And it follows 9 minus 5 is 4, right? So that gives us the correct answer. 9. Remember, we have learned previously how to divide by 11 and by x plus 1. So we can also use that instead of doing the first by the first and the last by the last, and in combination with argumental division, or the reverse of vertical and crosswise multiplication, or by multiplying by 11, we can just simply divide by x plus 1. So dividing by x plus 1, we get the running difference, right? So first, we bring down the first coefficient, which is 4, decreasing the exponent of x by 1. So now it's 4x squared. Then we subtract 13 minus 4 is equal to 9. And then 4 minus 9 is equal to negative 5. Negative 5 minus negative 5 would be 0. So this is an exact, the answer is exact. So 4x cubed plus 13x squared plus 4x minus 5 is equal to x plus 1 times 4x squared plus 9x minus 5. In chapter 34.2, again, this is special cases when one factor is x minus 1. So we've been doing when one factor is x plus 1. This time we'll be doing when one factor is x minus 1. This is similar to if x is 10, then this will be similar to 10 minus 1 or 9. Okay, a polynomial with a zero sum of coefficients has x minus 1 as one of its factors. If, for example, we want to factor x squared minus 3x plus 2. So we see that the sum of the coefficients is equal to 0. 1 minus 3 plus 2 is 0. So x minus 1 is a factor of x squared minus 3x plus 2. To find the other factor, we can again apply the first by the first and the last by the last. So we divide the first coefficient of x squared by x and the constant 2 by negative 1. X squared divided by x is x, and 2 divided by negative 1 is negative 2. So the other factor is x minus 2. X squared minus 3x plus 2 is equal to x minus 1 times x minus 2. For any trinomial ax squared plus bx plus c, if one of its factors is x minus 1, then the other factor is ax minus c. Now let's take a look at a longer polynomial. We have 2x cubed minus 4x squared minus 3x plus 5. Again, the sum of the coefficients is equal to 0. 2 minus 4 minus 3 plus 5 is 0. So, x minus 1 is a factor. Again, we can apply the first by the first and the last by the last. We can divide 2x cubed by x and 5 by negative 1 to get 2x cubed divided by x is 2x squared, and 5 divided by negative 1 is negative 5. So the other factor would be 2x squared plus bx minus 5. Now we don't know what b is again. But remember, we know how to divide by 9, and that's the same as dividing by x minus 1. So first, we copy the coefficient 2 and decrease the, since we're dividing by x minus 1, we decrease the power of x by 1. So now it becomes 2x squared. Then we add 2 to the coefficient of the next number. 2 plus negative 4 is negative 2. Negative 2 plus negative 3 is negative 5. Negative 5 plus 5 is 0, so that means that it's exact. There is no remainder. 2x cubed minus 4x squared minus 3x plus 5 is therefore equal to x minus 1 times 2x squared minus 2x minus 5. In fact, if we're doing this, we don't even need to apply the first by the first and the last by the last anymore, because this one's direct, right? Now let's take a look at another example. If, for example, we have an even longer polynomial and we want to factor it, x to the fourth minus 3x cubed minus 11x squared plus 3x plus 10. We see that the sum of the coefficients of the odd-powered terms is equal to the sum of the coefficients of the even-powered terms. So we see either that you have the even, you have 1 minus 11 plus 10 is equal to 0. And the odd-powered, you have negative 3 and 3. Negative 3 plus 3 is 0. So they're both equal and they're both 0. If they're equal, then x plus 1 is a factor, right? Since the sum of the coefficients is 0, then x minus 1 is also a factor. And we can divide by x plus 1 and x minus 1 to get the other factor, which is x squared minus 3x minus 10, which can be broken down further into x plus 2 and x minus 5. Now, let's talk about factoring using coefficients. Let's take a look at an example. Factor 6x squared plus 59x plus 144. Now, those are very big numbers, and that will be hard to factor. So what we do is that we use P as SP, or the product of the sums, is equal to the sum of the product. So we add the coefficient 6 plus 59 plus 144, which is 209. What are the factors of 209? That's 1 times 209. And if you remember your how to find multiples of 11, remember, you add digits and even digits. So 2 plus 9 is 11. Therefore, 209 is divisible by 11. So 209 is either 1 times 209 or 11 times 19. The product of the sums is equal to the sum of the products. Tells us that our factors, that the factors of 6x squared plus 59x plus 144 may have the combination 1 and 209 and 11 and 19 as the sum of the coefficients of the factors. So let's first consider the possibility that the sum of the coefficients of the factors are 11 and 19. So let's keep that in mind. Now we factor 6. The factors of 6 are 1 times 6 or 2 times 3. So knowing that 6x squared can be factored into x times 6x and 2x times 3x, we can now continue using 11 and 19, thinking of the sum of the coefficients of the factors are 11 and 19. So let's try using the combination 1 and 6 first. If the sum of the coefficient is 11, then 6x should be paired with 5 because 6 plus 5 is 11. But if we want it to be the sum, if we want the sum of the coefficient to be 19, then 6x should be paired with 13 because 6 plus 13 is 19. But 5 and 13 are both not factors of 144. So we can't have 6x plus 5 and 6x plus 13 as factors. So now let's take a look at the other factors, the 2 times 3. If we want the sum of the coefficient of the factors to be 11 and we have 2x, 2x should be paired with 9 because 2 plus 9 is 11. If we want the sum of the coefficients to be 19 and have 2x, it should be paired with 17 because 2 plus 17 is 19. But again, we take a look at 144. 17 is not a factor of 144. So it can't be 2x plus 17. So it should be 2x plus 9. And now, let's take a look at the partner of 2x plus 9. So if the sum of the coefficients of 2x plus 9 is 11, then the other one, the other factor, should have a sum of coefficient equal to 19. And of course, the partner of 2x is 3x. So it should be 3x plus 16. So the factors of 6x squared plus 59x plus 144 is equal to 2x plus 9 times 3x plus 16. Let's use the technique of factoring using coefficients to solve another problem. Example, we have x to the fourth plus 4x cubed plus 8x squared plus 8x plus 4 is a perfect square. Find its square root. So first, let's write it again. Since it's in the fourth power, obviously the square root of that would be ax squared plus bx plus c. So we can use the first by the first and the last by the last. We can find the square root of the first term and the last term. The square root of x to the fourth is x squared, and the square root of 4 is 2. So we know that the square root would be equal to x squared plus bx plus 2. Okay, so there we go. Now we can factor using the coefficients, remember? Let's write it like this. So we add the coefficients of the left-hand side. We have 1 plus 4 plus 8 plus 8 plus 4. And then that would be equal to the square of 1 plus b plus 2. 1 plus 4 plus 8 plus 8 plus 4 is equal to 25. 1 plus b plus 2 can be simplified into 3 plus b, so that's 3 plus b squared. 25 is 3 plus b squared. We know that the square root of 25 is 5. Therefore, 3 plus b is equal to 5. And we can easily solve for b. b is obviously 2. So the square root of x to the fourth plus 4x cubed plus 8x squared plus 8x plus 4 is x squared plus 2x plus 2. That was quite easy and unexpected, right? So I hope that as we have discussed so many things, you'll be more adventurous in trying to find ways to connect your basic arithmetic to algebra and finding good solutions. Sometimes we may think of solutions. They may not be the easiest, but it at least offers us more ways of solving. Thank you for listening. We hope you enjoyed the selection of lessons from our book, Algebra Made Easy as Arithmetic. Virgilio I. Prudente, the author of Algebra Made Easy as Arithmetic, is an educator, speaker, and certified teacher of Vedic Mathematics Academy, UK. He hopes to train 100,000 math-loving students by 2020. He created the MATH-Inic system to make math fun, fast, and easy. He preaches popular math by teaching MATH-Inic, writing books, and conducting math workshops for parents, teachers, students, and underprivileged children. You may read more about his two books, The 25 Math Shortcuts and Algebra Made Easy as Arithmetic, and how we introduce and promote Vedic maths in the Philippines at www.math-inic.com. Again, this is Veronica Prudente of MATH-Inic Philippines. helping deepen the understanding and appreciation of numbers. Thank you and good day.